Hi all, welcome to the part 2 of today's lecture. Uh, we are talking about divergence and curl. Now we talked about what divergence is and we did few examples. Now the last thing about divergence is its connection to flux. Now if you remember, divergence measures how much the rate of fluid flowing out from a point, and flux measures the amount of fluid flowing out through a curve. So they are definitely related. Now the divergence of F at a point, say point A, is the rate of fluid flowing out. Rate fluid flowing out from A. Now what we are going to do is, for each point you have a flow and you add them together. So the sum of divergence through over all the points in D, over all points in D. Okay, so it's an infinite sum. You can kind of approximate it with an integral, a double integral, since this is two-dimensional. Divergence, it is the total amount of fluid flowing out from the curve. So this is the total fluid flowing out from the curve C, which is the flux, right? So what we get is the flux is in fact the divergence. Okay, flux by definition is Px plus Qy. Okay, this is actually, it's not the definition, it's from Green's theorem. Flux form of the Green's theorem says the flux equals that, and we saw P sub x plus Q sub y is the divergence. So this is the double integral of divergence. So the flux is the double integral of divergence. Okay, so we talked about what divergence is and how to use it to do calculations. Now let's move to curl. So curl of a vector field F is defined to be the cross product. Now remember, divergence was the dot product of the gradient operator with the field. Now curl is the cross product. Now as soon as we have a cross product, it's no longer a number, it's a vector. So curl of F is a vector. The divergence of F was just a number or a scalar. Curl is a vector. Okay, so the cross product can be calculated using the matrices determinant of a matrix, which is the ith component is dabba r over dabba y minus dabba q over dabba c. Then the second component is negative dabba r over dabba x minus dabba p over dabba z. The last component is dabba q over dabba x minus dabba p over dabba y. In much simpler notation, r sub y minus q sub z. Then you can distribute the negative sign, p sub z minus r sub x, q sub x minus p sub y. Now this is the definition of curl in 3 dimensions, so in R3. Now if you want the curl in 2 dimensions, you just plug r equals 0. So for 2 dimensions it is, so let me use a different color. So there is no component with respect to z. Now think when you take the cross product, you get the perpendicular vector to both vectors. If this is in 2 dimensions, the perpendicular will be the third dimension. So the 2-dimensional version is qx minus py times k in the direction of the other dimension. So this is in R2. So to be complete, let me write curl of f equals that. Now if you are working with a 3-dimensional vector field, use that. If you are working with a 2-dimensional vector field, you can use this. Okay, so now we can look at the physical interpretation. So, physically, curl measures the rotation around the point. Curl of f at point A is the rotation around the point A. Okay, so in a sense, if you have a radial vector field, then there will be no rotation. For an instant, think about gravity. So if you take a particle in the space, the forces around it actually balance out so that it will never rotate. So the curl is 0. That is the idea. Okay, so let's do a few examples. Example number 52. Find the curl of this vector field. Okay, so the curl of f is the determinant of the matrix I, j, k by x dabba over dabba y dabba over dabba z, then x grad z e y plus xc and x y z. Now for me it's easier to memorize this rather than memorizing this equation. Two-dimensional motion, it's easy to memorize. So if you are working with a three-dimensional vector field, it's easier to use the definition of cross product. Okay, so the components will be first these two, so derivative with respect to y, it's xc, minus with respect to z, it's x. So I used these two to find the first component. Now to find the second component, it's negative yz minus x squared. So I use these two to find the second component. And finally the third component, z minus 0. I use these two components, these two, to find the third component, right, which is xc minus x, x squared minus yc, and c. So this is the curl of f. Example 53, find the curl of y comma 0. Okay, so let me draw a picture. Now the x component is the y value. So on x-axis it's 0. If I move 1 towards y, you get arrows of length 1. If you move 2, you get arrows of length 2. And if you go further, you get much larger arrows. And if you go negative, the directions change. Now, just by looking at the picture, we can decide whether there is a rotation. Think about a point. Now the force or the flow on top of that point is much larger than the flow below it. So what happens is, now think, on top of the point there is a much higher force than the bottom. So effectively it will rotate in this direction. Now using the right hand rule, the vector of rotation is going towards the screen. If you are rotating in clockwise direction, use right hand rule. Then the thumb is directed inside the screen, so the vector should be inside the screen, or a negative k. We don't know exactly what the number is. It should be some number times negative k. Okay, so let's actually calculate it. The curl of f, now since it is two-dimensional, you know it's qx minus py times k. Q sub x, it's 0, q is 0, p sub y is 1. So the answer is negative k. Now another way to think is, if you let's say this is a river and the arrow shows how the fluid is flowing. If you put a particle in the place of this red dot, what will happen? How much rotation will be there? So think you are placing a leaf in the red color dot, then it will definitely go towards right because all the arrows are pointing right. So the leaf will flow towards the right, but it will be rotating slightly. So as time moves on, the leaf will move towards right with rotating clockwise. Curl calculates the rotation part. Okay. Now the curl is connected with the rotations, and it is similar to divergence. Remember, divergence was connected with the flux. Curl is connected with circulation. Now the circulation by Green's theorem is the double integral of qx minus p sub y. This is by Green's theorem, the circulation form. Now you can see the connection between the thing inside the integral and the curl. You are missing only the factor of k. So let me add the factor. Now to make it just 1, I just take the dot product of k by itself. Okay, so now this part is the curl. So the double integral of curl of f with the dot product with k. So the circulation is the double integral of curl with the dot product. Okay, another example. This is a slight variant from the book, so I named it 54 prime. Show that the radial field F has no spin. Okay, so this is the thing I told about the gravity. So the vector field looks like this. It is flowing out from the origin, and when you go farther away, the flow becomes larger. Now if you place a point somewhere here, now the flow on the right side of the point is the same as the flow on the left side, so it's not rotating at all. It will be moving in that direction, but it will not be rotating. So curl is 0. Now to show something has no spin, you show the curl is 0. To show there is no spin, we show curl of the field is 0, and it's 0 vector because curl f is a vector. Now let's calculate the curl of f. It is q sub x minus p sub y times k. Q sub x, so q is y, p is x. Now the partial derivatives are in fact 0. Q does not depend on x, p does not depend on y. So you get 0 vector. Therefore, the radial field x comma y has no spin in it. Right? Now we did we did few examples using curl. Now let's look at the connection between curl and divergence. Okay, so what I'm going to do is calculate the divergence of curl of f and curl of divergence of f. Okay, so what this says is you take the field, you check the rotation field and see how much is. So on the left side we have curl of f, which means the rotation field. So you look at the rotation field of f, then you look at how much is flowing out from each point. Okay, before calculating the left hand side, let's look at the right hand side. Now the divergence is a scalar, right? Or just a number. Then you cannot take the curl of a scalar, because remember, curl is the cross product of the gradient operator with the field. So this is impossible. So it does not exist, or undefined. So you cannot operate curl and div in this order. But the one on the left hand side, the curl is a vector field. So taking divergence makes sense. So divergence is the dot product and curl is the cross product, right? Okay, now when you take the cross product, you get a perpendicular vector to both vectors. So the second term is orthogonal to the gradient field, sorry, gradient operator. Now when you take the dot product of two orthogonal things, you get 0. So the divergence of a curl is 0. Now physically what this means is, when you take the curl, you only consider the rotations, and it's now similar to the magnetic field, where the flow going from the point is the same as flow going towards the point. We only collect the rotation in the field. Okay, so let's do an example. Show that this field f is not a curl of any vector field. Okay, so let's suppose it is a curl. If f is a curl of some vector field, that means f equals curl of some other vector field, let's say g, then the divergence is the divergence of curl of g needs to be 0. If f is a curl of some vector field, its divergence needs to be 0. So let's calculate its divergence. Divergence is you differentiate each component with respect to corresponding variable. So it's ex, the first part, second one is c, third is 2xc, which is non-zero. Okay, if f is a curl of some vector field, divergence needs to be 0, but we saw divergence is non-zero, so f is not a curl of any vector field. Okay, now the last thing for this section is connection between curl and conservative fields. If f is a conservative field, then the curl of f is, okay, by definition it's the cross product Remember, if it is a conservative field, then we can write it as nabla f, where this f little f is the potential function of big F. Now, you can think this as taking cross product of the same vector, nabla and nabla. Okay, so the cross product of same vector is 0. If you remember, to find the cross product, you use sine theta, where theta is the angle between them. Since we have the same vector, the angle is 0, so sine value is 0. Therefore, curl of a conservative vector field is 0. Now, this can be seen because, okay, curl of f is if you remember, it has 3 components, and each component was the difference of 2 partial derivatives. For an example, the first component was, so it is q sub z minus r sub y. The second component was, okay, let me write it, r sub x p sub z, and the third component q sub x p sub. Okay. In curl, this was the 3 components, and if it is 0, that means you get qz equals ry, pz equals rx, and qx equals py. Now this is the cross partial property. So if the curl is 0, then the cross partial property holds. That is the reason we get what we have in the top. Conservative fields follow cross partial property. Okay, that is the end of this section. There will be a third video where you will get 10 minutes to complete the quiz for today and yesterday's material.